top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. A photoelectric diode consisting of a potassium cathode of work function energy 2.00 electron volt is illuminated by monochromatic light. The stopping potential of the emitted electrons is found to be 0.48 volt. What is the wavelength of the illuminating light? The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. The fundamental physical component is the photoelectric diode. So we could write that the concept is the photoelectric effect. More fundamentally than this, however, it would be correct to say that the fundamental physical concept is the quantization of light. The next step of the interpretation is to create the model and represent the model in a diagram. The model of our photoelectric diode consists of a cathode, monochromatic light, and the application of a stopping potential to measure the maximum kinetic energy of the emitted electrons. In our model, we draw the cathode. Our cathode is illuminated by monochromatic light. For the quantization of light, it is the frequency of the incident light that is of importance. The incident light causes the release of photoelectrons from the cathode. We will consider those electrons that drift from the cathode to the anode. The important parameter of this beam of electrons is the maximum kinetic energy that is predicted by the quantization of light. We should note that Kmax refers to the kinetic energy of the electrons immediately as they are emitted from the cathode. Lastly, we show the application of a potential difference that would impede the flow of electrons from the cathode to the anode. At the so-called stopping potential, the flow of electrons from the cathode to the anode just ceases. The third step of the interpretation is to extract the data carefully from the problem. We are told that phi, the work function energy for the potassium cathode, is 2.00 electron volt. We are also told that the stopping potential is 0.48 volt. We therefore write down that phi is equal to 2.00 electron volt, and that V stopping is equal to 0.48 volt. As our first calculation, we can write down that the maximum kinetic energy of the electrons, Ke max, is equal in electron volt to the stopping potential in volt. We therefore write down that Ke max is equal to 0.48 electron volt. The first step of the strategy is to determine precisely what is required. We are required to find the wavelength of the illuminating light. In our solution, we'll call this required wavelength lambda. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. The fundamental idea behind the photoelectric effect is that one photon of light imparts all of its energy to one electron. This photon energy therefore becomes shared between the energy that is required to release the electron from the cathode and the remainder, which becomes the kinetic energy of the emitted electron. The maximum kinetic energy of the stream of electrons is obtained from those electrons that were initially at the highest energy within the cathode. That energy is given by the width of the forbidden zone within the cathode, which is given by the work function energy phi. From the quantization of light, the energy of each photon is given by the frequency of the incident light, or alternatively, the wavelength of the incident light. The third step of the strategy is to create an action plan based on the concept map. In this problem, we're given the work function energy phi, and we obtained the maximum kinetic energy from the stopping potential. We are required to find the wavelength lambda. So as our plan, we use the maximum kinetic energy of the electrons and the work function energy phi to find the energy of each photon of the incident light. We then use the energy of each photon to find the frequency of the incident light, and then we use this to find the required wavelength. The first step of the execution is to follow the steps of the action plan. First, we find the energy contained within each photon. We will use an equation that is better known as Einstein's photoelectric equation, but which from a fundamental physical concept is the conservation of energy during the transfer of energy from the photon to the electron. We therefore obtain that the energy of each photon is equal to phi plus Ke max, which is equal to 2.48 electron volt. In this calculation, we're going to keep 3 significant figures throughout the calculation and only report our final answer using 2 significant figures. Next, we use the quantization formula for light to obtain the frequency of the incident light. In this formula, the energy of each photon is given by Planck's constant multiplied by this frequency. It is important to note that in this problem we are going to use electron volt as our unit of energy. We will therefore use the version of Planck constant given in electron volts. Using this, we find that the frequency of the incident light is 5.99 by 10 to the 14 per second. Finally, we use the equation from the wave property of light, that the speed of propagation of light c is equal to the frequency times the wavelength. From this we obtain that the required wavelength is 5.01 by 10 to the minus 7 meters. The second step of the execution is simply to write down and highlight your final answer. So here we write down our final result. As mentioned earlier, we will write down our final result using the 2 significant figures that is given in the problem. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. We are asked to find the wavelength of the incident light, and we have given this wavelength in meters, which is the correct unit for wavelength. We also notice that this wavelength is 500 nanometers. This wavelength falls within the range for visible light. This is therefore a reasonable order of magnitude for our final answer. Here once more are the 3 steps of our problem-solving method. Thank you for watching.